Hey, welcome back, my little bowls of gravy. We are going to carry right along to our third lesson in this wonderful trig unit. We're going to talk about solving trig equations today. I think that you will like this one more than you have liked the last two. The reason for that is because it's a lot more... it's very similar to what you've already done in your life. So the amount of new stuff you have to do is not quite as drastic as the amount of new stuff you had to do for the last two lessons. In this lesson, you will be solving stuff, and you guys are generally pretty good at solving. So let's go take a look at one thing I just want to mention real quick, and then we will do a couple of examples just to get you folks familiar with what you're doing, and then off to the homework, right? All right, so let's talk about, just for a moment, the difference between what we've been doing and what we are doing now. Okay, what we have been doing is verifying or just messing around with trig identities in general. The difference between these things is the fact that we've been using identities, and identities are true regardless of the value of x. So let's look at this equation right here. Regardless of what value of x we plug in here and here, this thing is always true. If you do sine squared of 36 degrees plus cosine squared of 36 degrees, this guaranteed will equal 1. It doesn't matter. As long as it's sine squared and cosine squared of the same angle. This is true 100% of the time, and you could put any number you want there and there. Okay? This is what is called an identity because it is always true. Okay. This is just a regular equation because if we look at sine of x, like even if we look at a graph of sine of x, right? Sine looks like that, vaguely, right? This is 1. This is -1. This should touch right there. And right there, this spot is pi over 2. So we can't plug 36 degrees into x right there and expect this equation to be true right now. It only works at certain ones. The observant of you will be shouting at me, right? You're going to say, but Mr. Barton, don't trig functions repeat? You're right. So there is another one here, right? Right there. This would be 5 pi over 2. And then there's another one at 9 pi over 2, and there's another one at 13 pi over 2. There are actually infinite values of x that we could put in here. There's a list that we could make: pi over 2, 5 pi over 2, 9 pi over 2, etc. All right. This list goes on forever. But don't confuse that for thinking that all of the values of x work, right? Pi does not work. This does not equal 1. It's not up there. This does not equal 1. This is at 3 pi over 2, right? And right there at 2 pi, it's not equal 1 either. So there are an infinity number of places where this is true, but it's not true everywhere. So what you're doing today is you are finding the places that it is true and telling me that. Okay? So we're not going to trip too much about the infinite list here. Really what I'm going to want is maybe like the first one. Or if I get really creative with making your problems for the homework, I might put which one of these is not a solution. That would be kind of interesting, you think? But anyway, so the difference here is this is always true, and we've been messing around with identities for the last couple days, just seeing what they can do. Now what we're doing is looking at something that is not always true and finding when is it true. And that's what your goal for today is. Okay. Some of them can be a little tricky. Some of them not as bad. Some of them don't even have answers. So let's go look. All right. So here's our first example. You're going to have to pardon my lack of color coordination. That example number 1 should definitely be purple. But, you know, nobody's perfect. Anyway, so we want to solve this for x. We're trying to get the x by itself, and we're trying to figure out what values of x can we use, right? So, like all solving, your goal here is to get the x by itself. So we're going to think of the x being inside the sine function. So let's try and just get sine of x by itself first, right? So we're going to move this minus 1 over by doing the reciprocal, or not the reciprocal, the inverse operation. So we're going to move the 1. So we have 2 sine of x equals 1. And then this 2 is just multiplying to the sine of x. So we're going to divide both sides by 2. All right, these cancel. So we have sine of x equals 1/2. Now, there's a couple of ways that you can go about doing this. What you can do to get one of the solutions, what you can do to get one of the solutions, sorry, I had to think about how I want to teach you this, is you could do an inverse sine on both sides, like on your calculator, right? Cancel that, cancel that. So x equals the inverse sine of 1/2. And your calculator will spit out a number, right? It will spit out, what is the number? It'll spit out in radians, pi over 6. Okay, that's because on our unit circle, if we go right there to 30 degrees, or pi over 6, we are at radical 3 over 2, 1/2. All right, cool, pretty neat. So we have that answer. But we can see, because sine is the y coordinate, there's another 1/2 right over here. This isn't even that far away, and your calculator, I don't think, will tell you that value. So let's at least get all the numbers in the first 2 pi, and we'll ignore all the repeated values, right? So this other one, where sine is equal to 1/2, is going to be at 5 pi over 6. These are the two solutions that are within the first period of this operation right here. Like I said on this slide, because sine repeats, you can get more answers than just those two. What we're looking at, oh shucks, is not blue. Let's do red. Okay. What you are looking at on the next problem is this spot and this spot. So basically, you're looking for the two places where our sine wave is at negative or at positive 1/2. So you've just found there and there. Okay, so not so bad. If you want to generalize these so that you include the like infinite repeated solutions, notice, maybe not notice, but the trick to getting these answers are, because it's at 1, the next time that it's going to happen is 1 full period away, and the period of sine is 2 pi. So what I did is I just did plus 2 pi over and over. Okay, and because this trig operation that we just looked at also has a period of 2 pi, what you can do to get the infinite solutions are you can take your two solutions from the first period of your graph or of your function, and you can say pi over 6 plus n times 2 pi. What this n is, n in math means any integer. So it could be like 2, 3, 4. So you add any number of 2 pi's to this, and you'll get one of those other repeated solutions. Same thing with this one. You would just do 5 pi over 6 plus n, so any number you want that's an integer, times 2 pi. So any number of 2 pi's. You can do 2 pi, 4 pi, 6 pi, so on. Okay? So on your homework, I'm probably only going to ask you for these just to avoid confusion and complications, but realize trig functions do repeat. All right. So let's look at this one. This is just a slightly more complicated one. That's what we're going to do from now on, is we're just going to make them a little harder, just so you kind of ease into the solving. So like you have done with pretty much all your equations in your life up until now, one really great strategy is get the x's alone. So what we're going to do is we're going to move this over there so that our x's are on the same side. And then we'll move this radical 2 over there to move the numbers away. Just like if you had x plus 2 equals negative x, right? You'd want to move the x's together and move the 2 away to be able to solve it. So let's add sine of x to both sides. And then let's subtract radical 2 on both sides. So sine of x plus sine of x, this works very similar to just like x plus x. This would be 2x. So sine of x plus sine of x, this would be 2 sine of x. Equals, these cancel. Negative sine of x plus sine of x cancels. And then you don't have anything to subtract from, so it's just negative radical 2. Okay. Now we're still trying to get the x by itself, or at least the sine of x by itself. So we're going to divide both sides by 2. Okay. So these cancel, and we have sine of x equals negative radical 2 over 2. Okay. Luckily, this is one of those numbers that's on our unit circle, so it should be pretty easy for us to just think a little hard and get our x values. So let's remember that sine is the y value of your unit circle. So we want the y's to be negative radical 2 over 2. And radical 2 over 2 happens at the 45 degrees ones. So it'll be right there and right there because they need to be negative. So they need to be on the negative side of the y-axis. So this one right here is 5 pi over 4. And then this one right here is 7 pi over 4. Okay. So again, we could add the plus n times 2 pi to both of these to make them super general. But as long as we get all the solutions in the first 2 pi, I'm going to be happy with that for right now. All right, let's look at another one. So here, this one looks pretty intimidating just because we have cotangents and cosines. So in general, there are going to be 2 strategies, right? You're either going to try and turn one of these trig operations into the other one so that they combine, like turn cotangent into cosine somehow, or cosine into cotangent. Or you're going to try and separate them into separate terms, meaning like you've got your cotangents here and you've got your cosines here. And then we want them to equal 0. So you, just like you have like x plus 1, x minus 2 equals 0, you set this factor equal to 0, this factor equal to 0. You could do the same thing with these as long as we split them up. And this is actually the method we're going to shoot for in this problem. Okay. So what we're going to do is we're going to try and set this equal to 0 and then factor. All right, sorry, let me just fix my pens here. Okay. So first, let's move this 2 cotangent over so that we have it equal to 0 like we want. So we're going to do minus 2 cotangent of x minus 2 cotangent of x. So these cancel and this side is 0. On this side, this is a cotangent and this is a cotangent, but what is cosine squared x minus 2? You have no idea. So we're going to just leave these separate for right now. So we have cotangent of x, cosine squared of x, minus 2 cotangent of x. Now you can see that we have a cotangent here and a cotangent here. So these are a common factor of this term and this term. So we're going to factor out the cotangent. So we have cotangent of x times cosine, if I could spell, cosine squared x. Let me clean that up so that you guys don't yell at me. Cosine squared x minus 2 equals 0. So now we have two factors being multiplied together, and they equal 0. So we can just set this equal to 0 and this equal to 0, and then solve for x that way. So let's split them up. So we're going to have cotangent of x equals 0, and we're going to have cosine squared x minus 2 equals 0. For cotangent of x equals 0, what I would do is I would maybe graph this and look at it to find where does this graph equal 0. Because again, if you hit it with like an inverse cotangent, if there are multiple solutions, you might not get them. But for tangent and cotangent, because of the shape of the graph, you don't really get more than one solution per period. Like let's look at cotangent. Cotangent looks like this. So right there where it equals 0, that's the only place it's going to equal 0 on this whole section. So there's only one solution. It happens at x equals, I believe it's pi over 2, yeah. Okay. One thing I want to mention about this is because the period of tangent and cotangent is only pi, that trick to generalize this so that you get all the solutions, it would be plus n pi, not 2 pi, because it repeats every pi. All right, so this piece is just because it's a cotangent and not like a cosine or a sine. All right, for cosine squared of x minus 2 equals 0, let's move the 2 over. So we'll add 2 to both sides. These cancel. So cosine squared x equals 0. And then we can take a square root of this. So cosine of x equals plus or minus, because we took a square root of 0, but it's 0. So negative 0 is 0. So we want, I'm sorry, back up before I make a terrible mistake. 0 plus 2 is definitely 2, not 0. Sorry, I almost made a terrible mistake. Okay, 0 plus 2 is 2, square root, cosine of x equals positive or negative radical 2. Okay. Be very careful here. I know you guys are tempted to look at all the 45-degree angles, but this is not radical 2 over 2. This is just regular radical 2. So regular radical 2 as a decimal, this is 1.414. Cosine of x, if we think about the range of this function, let's look at a graph of it. Cosine is going to look like that. This maximum here is 1, and this minimum is negative 1. This question is asking you, when does your graph equal 1.4 and negative 1.4? Your cosine will never touch either of these two lines because the maximum and minimum of cosine are 1 and negative 1. It's not in the range, meaning there is no input of cosine that can give you this output. So the solution to this part of our equation is that there are no solutions from this. This there is no solution. So this whole side kind of just gets thrown away. You go, well, we checked it, but there aren't any solutions there. This is never true. So our only solutions for this are right here. So x equals pi over 2 plus any number of pi's, plus 1 pi, plus 2 pi's, plus 3 pi's, whatever, right? Okay, cool. So this is your solution. On your homework, it would probably just say x equals pi over 2. All right. Very last example we're going to talk about is one that's kind of, it's not so bad. It's not bad, but I don't know that you'd necessarily be like, oh, I could do that right away. So let's look at this. This thing is a quadratic. It's just the x's are signs. So we have basically 2x squared minus x minus 1 equals 0. And then there's like a little aside over here that says like let x equal sine of x, right? You just replace your x's with signs, and it's the exact same thing. So what we're going to do is we're going to solve it the exact same way. We're going to factor this and then set the factors equal to 0. So luckily, I have factored it on a separate piece of paper. What I would do is probably like monkey method or box method, where you multiply that number back there, do simple factoring, then divide by the original coefficient. But if you have questions about that, go to the WebEx and ask me. I don't want to make the video longer than it needs to be. And you all laughed, right? You're like, is Barton making a short video? That's hilarious. So this thing will factor to 2 sine of x plus 1 times sine of x minus 1 equals 0. Okay. And we could check this, right? 2 sine of x times sine of x is 2 sine of x squared. 2 sine of x times negative 1 is negative 2 sine of x. And then sine of x plus times positive 1 is plus 1 sine of x. So negative 2 sine plus 1 sine equals negative 1 sine, which is that right there. And then 1 times negative 1 is negative 1. Wonderful. Okay. So we have that factored. Now what we're going to do is the same thing we do in any factoring problem, is we're going to take our factors and individually set them equal to 0. So we're going to have 2 sine of x plus 1 equals 0, and then sine of x minus 1 equals 0, and we're going to solve both of these equations. So on this first one, we are going to subtract 1 on both sides. These cancel, so we have 2 sine of x equals negative 1. Divide both sides by 2. So sine of x equals negative 1/2. And then if we look at this side, we just add 1 on both sides. And sine of x equals 1. So now what we're looking for is we are looking on our unit circle for all the places that sine of x, which is the y component of the unit circle, we're looking for all the places y is negative 1/2 and positive 1. Let me do this over here. Put that over there. So we have, obviously right there, that's the only place it happens to be 1. So sine of x equals 1. This angle right here that gives us that value is pi over 2. So x equals pi over 2. Then for the negative 1/2, we are looking at this angle and this angle. So these two angles are, sorry, I wrote them down. They are 7 pi over 6
And
11 pi over 6. Okay. So these are our three solutions to the equation in the first 2 pi or in the first period of our sine function. So there you go. There's 4 examples. Hopefully they're not too bad. Your homework is going to be pretty much just more of that stuff. So in general, your kind of tips are try and move everything to one side, move all the trig to one side, and then move all the numbers to the other side. If you have something that has multiple trig functions, try and factor it out. And then if you have anything really crazy, maybe ask your math teacher. I bet that dude could help. So until next time, I gotta find a better sign off, you guys. Anyway, have a good day.